Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is stability analysis in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also technical support and sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Cisco Cho will be your moderators, answering any questions you may have. They are both technical support engineers, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within this same dialog box. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. So as far as the content over the next hour today, I do want to just give a brief description of our structure stability add-on and some of the advantages that you'll find when you activate this within the RFEM 6 program. We'll then move on to our first examples, where we will show a simple member and plate verification example compared to the Euler buckling formulas. Moving on to our third example, this will be a 3D structure modeled with all beam elements. So we'll carry out the stability analysis there. Then moving on to a 3D surface model, this will be a tank type structure where we'll carry out the structure stability and talk about options such as imperfection modeling. We do have the ability to integrate the torsional warping 7 degrees of freedom also with the RFEM 6 static analysis, but the structure stability as well. One of our last examples today will be the steel joints add-on. So we'll take a look at how the structure stability can actually influence the buckling analysis as well on a much smaller scale with an FEA steel connection. And finally, this add-on is not only used for stability and buckling modes, but we can actually utilize it to troubleshoot instabilities for modeling errors. So to begin, when looking at the structure stability, this is an optional add-on within the RFEM 6 program. This allows us to run an eigenvalue analysis to determine the critical load factors in eigenvectors, or in other words, the buckling modes of our structure. Therefore, we can evaluate the stability of the structural system in regions prone to buckling. So when we're talking about regions prone to buckling, we're typically referring to very slender beams or columns or thin-walled thin-walled shell or plate elements. Now, everything that we'll be carrying out today will be according to a linear eigenvalue analysis, which we'll talk a little bit more in the next slide, but keep in mind that a nonlinear stability analysis is also available where we can actually increase the load increments to see the failure of the structure. As already mentioned too, not only can we look at the buckling modes of the structure, but we can carry out instability troubleshooting to locate modeling errors with a load-independent eigenvalue analysis. Now, of course, through all of these examples to see, we'll see the graphical rendering of the stability modes as we see over here on the right-hand side. Then we can integrate for further capabilities within the static analysis, such as applying structure imperfections. We can import effective length factors, and we'll see those carried out in the further design examples. Now, when we do activate this add-on, we have 3 analysis types available to us. The first is the eigenvalue method, or a linear analysis. And this is essentially where the buckling modes are determined through a linear method. If we have any nonlinearities defined, either material or geometric nonlinearities within the model, these are internally converted to linear elements in order to carry out the stability analysis with constant stiffnesses. Now, alternatively, we do have the incremental method with an eigenvalue analysis. So this is nonlinear and will take into consideration all geometric and material nonlinearities. Essentially, we will carry out the failure criteria and nonlinear effects, and these will be included during the incremental loading increase. We will find the last stable state with this nonlinear analysis to carry out the linear stability analysis, or the eigenvalues. The third option here is the incremental method without the eigenvalue analysis, also nonlinear. This is identical to option number 2 with that nonlinear analysis capabilities. We just simply won't carry out the eigenvalue analysis within that last stable state. So with all of our examples today, we will be utilizing the linear eigenvalue method, but just keep in mind if you do have those nonlinearities, it's capable within the add-on to also utilize these nonlinear options. So beginning here with our first example, we will begin with a single column element. And we really want to compare to the Euler buckling equations here for this column. It's a W8 by 35. We see the cross-section property shown here over on the left. Modulus of elasticity for the material is 29,000. The height of the column is 12 feet, and we've modeled it here with a pin roller or a pin roller type situation. So pin at the bottom, roller at the top, free to deflect in the vertical direction. And we will apply a single vertical load at the top here for that compression of 100 kips. Now, when we look at the Euler buckling formulas shown over here on the right-hand side, we have both the strong axis where we can simply input in the properties of the section and the material to determine that our critical buckling load for that strong axis direction is around 1753 kips. For the weak axis direction, when we modify this input here, we find, of course, a much smaller critical buckling load of 588 kips. It should be known that in the RFEM model that I'll show you in just a minute that the shear stiffness is deactivated for this comparison. It is possible within these formulas to take into consideration this shear stiffness, but it gets a little bit more complex. So just for ease of comparing these two examples, we'll go ahead and deactivate the shear stiffness. So as we look at this example here within RFEM 6, our main base program, we can see this W section profile with the 100 kip load applied at the top, the pin roller type scenario, 12 feet high. So we want to activate the structure stability add-on, and we can do so within our toolbar by accessing our base data, or we could right-click on the model name here to also access that base data dialog box. And under the second tab are all of our available and optional add-ons. So for today, we're going to be utilizing the structure stability add-on. So when I click OK, pretty much nothing changes within the model itself here, but we can go into the load cases and combinations dialog box. So I currently only have one load case defined with that 100 kip load applied at the top of the column. And this will be carried out according to a first order static analysis. But we can activate the structure stability add-on with this checkbox down here at the bottom. So looking at the default definition types, you'll notice that there are two definition types that are immediately set. The first is an eigenvalue method linear analysis, which we should recognize from the PowerPoint. We'll go ahead and carry out that linear analysis for today. And then we can set the number of eigenvalues to solve for. So the default is 4, but we could increase this manually or decrease it just depending on our model. The second default setting here is identical. It just has a higher number of eigenvalues set to 10 here by default. So carrying out the linear analysis with 4 eigenvalues, we'll go ahead and click OK. And to run this calculation, so we're going to initially calculate the static analysis with this first load case, but then you'll notice that we will carry out the second calculation here for the stability analysis. So we're not so interested in the static analysis results, but immediately we jump to the stability analysis results that are now available to us in our navigator. And when we look at the results here for the structure stability add-on, we will see 4 different eigenvalues that we have solved for. In addition to this, within the table, we'll also see the critical load factor given. So the critical load factor for this first buckling mode shape, which we can see is buckling out of plane in the weak axis direction, is the factor that we can multiply the applied loads, and in our case, it's 100 kips before we are going to see the structure fail, as we show here with this first buckling mode shape. The second mode shape is going to be buckling in the strong axis direction. And as expected, we see a higher critical load factor of 17.527. So again, we multiply by this factor by the 100 kip applied load in order to determine the critical buckling load. So we take this information back to the PowerPoint here to compare to the analytical calculations that we've carried out within this slide. And we can see that compared to the Euler buckling formulas with RFEM 6 comparison, we're getting a ratio of 1.0. So I think it's important to understand how we're carrying out this structure stability for simple flexural design here for the stability modes. Moving on to our second example, this is really very similar to what we just saw with our column, yet this time I wanted to utilize a 2D surface element. So members by default are represented by a single line element. Surfaces, on the other hand, are two-dimensional. So we have a 10-inch wide surface by 50-inch high. We also see the material properties over here, 29,000 KSI for the modulus of elasticity. The thickness is 1 inch. And again, very similar situation where we have pin supports at the top, at the bottom, and at the top we have a roller support that's free to deflect in the vertical direction only. So utilizing again the Euler formula shown over here on the right-hand side, we want to come up with the critical buckling load as a force per unit length to apply at the top of this surface. And what we find is that this is approximately 9.54 kips per inch before we should see this surface buckle. So we go into RFEM here to open up this example. And as mentioned, this is a two-dimensional surface. So we have 10 inches wide, 50 inches tall. I have left on the display here of the FE mesh, so you can see how that mesh will, how the structure will mesh this for this two-dimensional object. We also have a 1 kip per inch load applied at the top here. So very similar to the column, we want to go into the base data, and we can do so within the toolbar directly to activate under this second tab, once again, the structure stability add-on. We go into our load cases and combinations. And for this example, we have our single load case here with the 1 kip per inch applied as a line load at the top of this 2D surface element. We want to not only carry out the static analysis, but also the structure stability analysis. We'll go ahead and leave these default settings here for a linear analysis, carrying out 4 eigenvalues, and we can run this calculation. So the program would initially mesh a structure if we didn't already have it. It will carry out the static analysis, and then we move on to the stability analysis. So taking a look at our stability analysis results here within our dropdown, we see our 4 different mode shapes. And the first mode shape you can see here is buckling out of plane for this 2D surface element with a critical load factor of 9.566. So taking a look at these additional mode shapes, we can see here the deflected shape, but the critical load factor here is much higher. So in reality, we're most concerned with the lowest critical load factor. Now again, this is the factor, this 9.566, that we can multiply the applied load here of 1 kip per inch before we would expect to see structure failure or the buckling here out of plane. Again, we take this information back to the PowerPoint here to compare to the analytical formula, and we find a ratio of 0.997. Okay, so that should give us a better understanding then of, again, just the basic behavior of this structure stability add-on for a simple beam and a simple surface. Now let us go back into RFEM here to open up our third example. So this one should be a little bit more interesting, where we have a 3D structure that is composed entirely of beam elements. So you can see that all of these are member elements for our columns, beams, braces, represented by a single line element here. So no surfaces for this particular example. If we want to do a quick overview, the cross sections are from the AISC database. So we have W10 by 49s. We have some square HSS sections spanning between these moment frames, single angles for our cross braces here, lateral bracing. And we also have a very small taper for this beam member. And in particular, this is at 25% of the member length before it frames into the vertical columns. Now, to quickly take a look at the loading For this example, I have only 3 load cases defined. So we can view these loads here, and these are just general area loads created with the load wizard for dead load. If we're curious to see how the load distribution looks, we can right-click to display separately, and notice that I have created a one-way area load distribution so that the loads are mainly on these main beams here rather than the HSS spanning in the global Y direction. We can also view here the live load, same concept. If we want to view the area load instead, we can see this shown here on the structure with a varied magnitude. And finally, we have a projected snow load in the vertical direction. So for this example, I have applied only gravity loads. And I think it's important to understand that when we're talking about the buckling behavior of our structure, we certainly want to evaluate the worst case scenario where we have the highest compression forces in our members. And for example, in our column elements, we want to see the highest forces acting in the downward direction. This is typically with gravity loads. If we were to include, let's say, wind uplift forces, this is only going to do us additional favors in terms of the buckling behavior, because now we have introduced additional tension forces in those members. So again, when we are evaluating the structure stability, we really want to look at those downward compression, possibly gravity only loads. Okay, so I have additionally combined these load cases into load combinations according to the ASCE 7, and we can see those displayed here graphically along with the relevant load factors. I'm going to go into my load cases and combinations. Now, we certainly could activate here the structure stability for each individual load case, as we did in our previous simple examples. But instead, I'm interested in carrying out the buckling analysis for my load combinations instead, where I have combined all the load cases together. Now, the program by default creates 2 design situations based on the ASCE 7 2022 in this example. And you can think of a design situation as simply grouping together all of our factored load combinations. We can see this here, LRFD, according to the ASCE 7, as well as our second design situation, which groups together all of our unfactored load combinations. And this will eventually give us an envelope solution for those factored and unfactored load combinations together. Well, under the combination wizard settings here, I can go in and you'll notice that everything is solved here for our load combinations according to a second order analysis, but we have the ability to activate the stability analysis here directly within the design situation. And these default settings are identical to what we saw previously within the load cases, that we can carry out the linear analysis, and perhaps I increase this to 10 different eigenvalues to solve for this structure. So now that I have activated it within the design situation itself, I take a look at the load combinations individually listed out, and I can see now by default that the structure stability add-on is activated here. And that's just simply because I have activated that checkbox under the design situation itself. Now, by all means, we can come in here and individually carry out the structure stability for each individual load combination as well. So let us run through this calculation by running the Calculate All button. And as we will see, we will first run through the load cases according to first order, our load combinations using a second order analysis, but then we run through all of those load combinations again for the structure stability. So when we toggle this drop down to the design situation for our factored load combinations, again, this is nice because it's more or less an envelope solution for the static analysis. But you'll notice within this table here that shows our static analysis results for this design situation, we have the stability analysis envelope solution as well. The minimum critical load factor is 10.532, and the controlling load combination is load combination number 3. So this is kind of nice that, again, we don't need to run each individual stability analysis for each load combination and to manually check the results, but the program will give us the controlling load combination here. So we toggle down just to display the loads for load combination number 3, and no surprise, this is certainly going to be the controlling case because we have all 3 loads activated with the highest load factors to give us the greatest compression forces in our members. So we will toggle down to the stability analysis results for load combination number 3. And as we have input into the program, we had solved for 10 different mode shapes. Starting with mode shape number 1, we kind of see a racking here of this initial moment frame with a critical load factor of 10.532 as we were shown here within the design situation itself. And essentially, we're going to see here the flexural buckling in the strong axis direction of these columns. Looking at some of the additional mode shapes, we can see similar behavior just in different locations of the structure with a higher critical load factor. As we continue to increase, we may start to see more localized mode shapes. And what I mean by this, where we see the individual buckling of these columns, in particular in the weak axis direction. Whereas we compare to the mode shape before, this is maybe more of a global mode shape that kind of affects the structure together. Okay, so now that we are looking at mode shape number 1, let us focus in on this particular column here, and this is member number 10. Well, when we are looking at the stability analysis results within the table, we can use this drop down to view the results by member. So when I graphically click on this member here, the table updates to show me member number 10's results, and we have 10 different mode shapes shown here. And in particular for this first mode shape where we have failure of this column in the strong axis buckling, we can view the equivalent effective length factor, that K value, which is given as 3.012 in the strong axis direction. We also see here the effective length of 34.64. So if we plan to take this a step further and to design this structure, let's say according to the AISC or the CSA standard, and in particular, according to the AISC, we want to design it utilizing the effective length method. The effective length factors are really important. So we have the ability to get that information directly from the failing mode shape here. Now, when I take a look at these additional mode shapes, they're really not affecting member number 10 until I get down to mode shape number 7. And here we see the failure in the weak axis direction for member number 10. Well, we see the relevant effective length factor in the weak axis direction given as 1.008 and the effective length as 11.59. So assuming that we have already activated the steel design add-on within RFEM to carry out the steel design according to the AISC, information such as the unbraced lengths or effective lengths are always needed in order to carry out that design. And we do so by inputting in the effective length for the member directly. And I want to show you a nice feature here that, assuming again that we're carrying out design according to the AISC with that steel design add-on, we input our first effective length definition where you have the ability to import in from the stability analysis. So when I turn on this checkbox, I get a new tab here where for the strong axis direction, for consideration of, if we go back here to the main tab, flexural buckling about the major axes, we can import in that effective length factor directly from the stability analysis. So we choose here a load combination number 3. We will choose the mode shape number 1, and we can either graphically select member number 10 or we can choose it here within our dropdown, and notice that that effective length factor is automatically brought in as 3.01. We can do the exact same thing for the weak axis direction. Again, this is specific for member number 10. We will choose load combination number 3, but this time we want to choose mode number 7. And remember, that was where we saw this column fail in the weak axis buckling direction, again for member number 10. And we see that effective length factor brought in automatically as 1.01. So we don't need to do anything further here in terms of the effective length definition for flexural buckling in the strong and weak axis direction if we integrate this with the structure stability add-on. Okay, so now that we have covered the basic stability mode shapes here, keep in mind that everything that we have seen so far has been based on 6 degrees of freedom. And with 6 degrees of freedom in these various mode shapes, we notice that we're really only able to consider flexural buckling. And we certainly can see this with the mode shapes directly with flexural buckling failure of the columns themselves. But if we back up a step to look at the static analysis results or the internal forces from load combination number 3, what we'll actually see here is that we have pretty high bending forces along the length of our members. And when we look at our columns, we have pretty high axial forces, of course. And when we're talking about these bending forces, for example, for these beams, this should immediately flag us that possibly lateral torsional buckling is an additional stability failure state that we need to consider. So let us go back to the PowerPoint here to discuss these different stability failure modes. Now, we should be very familiar with the flexural buckling by now for our members. Ultimately, there's some critical buckling load for the strong axis and the weak axis before we see this member fail with flexural buckling. But there are also additional failure modes such as torsional buckling that has some other critical buckling load factor before we would see this member twist about its longitudinal axes. And this might be quite common for something like a cruciform section. Then we also have flexural torsional buckling. And when we have an applied axial force to the member on something like a single angle that's unsymmetric, then we're not only going to see this flexural buckling, but it's also going to be twisting about its axes. And of course, lateral torsional buckling is also a consideration when we have a bending moment along the length. So something like singly symmetric sections or unsymmetric, we're not only going to see it move out of plane, but also twist about its own axes. And the problem is that 6 degrees of freedom can only consider flexural buckling. Now, we can go ahead and say, well, if we are designing according to AISC or CSA, of course, the codes have analytical equations that are going to design for these additional stability failure modes. But this is in the design process. What I'm talking about specifically is with the static analysis as well as the structural stability. So how do we consider these additional failure modes? The answer is to enable the 7th degree of freedom or warping. And we have an additional add-on within RFEM 6 called torsional warping 7 degrees of freedom. So this allows us to consider the cross-sectional warping with an additional degree of freedom for member calculations. And what's nice is that everything is integrated automatically, including both with the static analysis, but also the structure stability add-on to determine additional member critical load factors and mode shapes. So again, 6 degrees of freedom can only consider flexural buckling failure. That's everything that we have seen up until now. I did want to put a quick note here that also with 6 degrees of freedom, the load application is always at the member shear center. So now when we enable that 7th degree of freedom, we can additionally capture the torsional, flexural torsional, and lateral torsional buckling behavior. And when we do enable that 7th degree of freedom, we get a load application at the center of gravity or the centroid of the member instead. What we will see in just a minute is that when we do enable this add-on, we do get additional options available to us, such as member transverse stiffeners to restrain the warping along the member length. Now, currently in RFEM 6, the 7 degrees of freedom is not linked in the steel design add-on when we're carrying out steel design according to AISC or CSA. It is currently linked for Eurocode only. We do plan to link those in the future to consider that 7th degree of freedom, but currently the full static analysis and the structure stability can easily consider the 7 degrees of freedom, which we'll see in just a minute. So just keep that in mind if we are taking that a step further with the steel design add-on. Okay, so what we will do here is to go back to the RFEM model, and we want to go into the base data here. Under the second tab, we will activate now not only the structure stability, but the torsional warping 7 degrees of freedom. When I do this, the program says it needs to delete the results, of course, because that was all based on 6 degrees of freedom. Now, by default, all of our members are considered free to warp. There is no warping restraint along the member length. In addition, if you would like the warping internal forces to be transferred to adjacent members, it's important here to create what we call a member set. So what I mean by this is that if we want the warping forces with the 7th degree of freedom to be transferred from, let's say, our beam on the right over to our beam on the left, we would need to hold down our control key to make sure both are highlighted here. We right click, and under the member option, we have the ability to create a member set. So that's just simply grouping those members together so that those warping internal forces will be carried out to adjacent members. Now, circling back to the warping restraints, we should see now under types for members, we have a few additional options here, including member transverse stiffeners. So I'd like to double click on this to create a few stiffener types for these members in order to restrain the warping at the member start and at the member end. And within this dropdown, we actually have several different stiffener types. For example, we can choose a flat plate where we could input in the material, we could input in the dimensions, and the program will automatically calculate the warping spring automatically to be considered within the analysis. For today, we will use this option at the bottom called warping restraint, where we will use the full warping restraint. And then I want to apply this to the member based on a certain percentage of the length. So I'm going to activate this warping restraint at 0% of the member length or the member start. And I'm going to add in a second warping restraint at the member end, so 100% of the member length. And then we can graphically select here which members we would like to apply this warping restraint. So I'll go ahead and use my selection box graphically here to select all of those main beams. I click OK. And once I click OK through this dialog box, you'll notice that we get a nice symbol shown here, which will represent where that warping restraint is located at the member start and the member end. So now we want to go to calculate all, and we have to rerun the static analysis now with 7 degrees of freedom. So we see the load cases carried out, but also those load combinations according to a second order analysis. Then we run through the structure stability again for all load combinations, and we should see slightly different results here. So number one, taking a look at the static analysis results, which we can view the internal forces here of our members, you'll notice that we have a few additional options now with that 7th degree of freedom. For example, we can view here the warping moment along the member length, or we can view as well the primary torsional moment and the secondary torsional moment. So this previously was not available with 6 degrees of freedom. Toggling down to our stability analysis, we also should see pretty significant or different results here as well. So no longer do our 10 different mode shapes look like what we previously saw with 6 degrees of freedom, but we see here the critical load factor is now 4.564, and our relevant mode shape is really focused here on these columns, and we can increase the size of this mode shape ever so slightly to see how this column has essentially flexural torsional buckling, where it is both kind of bending out of plane but also twisting about its own axes. So you can see that with the critical load factor, it's significantly decreased. Previously, it was around 10.5, and now it's only 4.564 before we're going to see the relevant mode shapes here. Now, when we look at these first four mode shapes, it's really flexural torsional buckling of these columns, but then we get into mode shape 5 with a critical load factor of 7.84, and this is where we begin to see lateral torsional buckling of those beam elements themselves. So again, when we are carrying out 6 degrees of freedom, if we're only concerned with flexural buckling, no problem, the program automatically considers this. But if flexural torsional buckling, lateral torsional, and torsional buckling are also a concern, then we really would want to consider enabling this 7th degree of freedom. All right, so this should give us a pretty broad overview now of member stability design. I now want to move into our next example to talk about surfaces. So you'll see here that I have a tank model, and everything is composed of 2D surface elements. So the tank wall is a surface element, as we see here, as well as the tank roof. To talk a little bit about the thicknesses and the materials, the entire tank wall and roof are going to be comprised of 1/2 inch thick A36 steel material. And then at the bottom here, we have an 8-inch concrete slab, 4,000 PSI concrete. I did want to point out that this file here, this structure, was entirely created using our block options up here in the toolbar. And when you take a look at the various block options, you'll see all the different categories for the different structure types, including silos and storage tanks. And within these options, as I kind of cycle through them, you'll see all of the various options that if I double click here, I have the ability to define the dimensions, the material, even some loading capabilities are automatically created. And that is how this example here was created automatically. For this example as well, we have only 2 load cases. We have a simple dead load where only self-weight is active, so no additional loads apply to this tank structure. And then we also have this fluid load, and the fluid load was automatically created with the block import option to represent, of course, some fluid at the inside of the structure acting with an outward pressure here against the tank walls. We also have a downward pressure acting at the base for the concrete slab. So I have left this with only these 2 simple load cases because actually for this load case number 2, the fluid load, we get pretty significantly high compression forces in our tank wall to carry out the buckling analysis. So therefore, I want to go into the load cases and combinations dialog box, and we want to carry out the structure stability here. A linear analysis, 4 different eigenvalues is fine for this particular load case number 2, the fluid load. And when I calculate this, the program will generate the FE mesh for our tank. It will run through the calculation for the static analysis, but then as well, we're going to run through the structure stability analysis for those 4 different eigenvalues. So once this is done here, we will see under the stability analysis, the relevant buckling shape. And I'm going to create a user-defined visibility here for only the tank walls, so we can see this in a little bit clearer form. And we have 4 different mode shapes that we have solved for. Notice that the critical load factor is quite low here at 2.882, and we see the relevant buckling mode shape. So kind of these localized buckling modes all around the circumference of our tank walls. Now, when I look at these additional mode shapes, the critical load factor is almost identical, around 2.8 or 2.9. Just simply notice that the location of these buckling modes is just changed ever so slightly. So when we back up a step here to just look at the structure in general, everything that we model in an FEA software is considered perfect. And what I mean by this is that everything that we have modeled considers that the manufacturing process is perfect, that when we essentially install this structure out in the field, it is perfectly aligned, but we know in reality that that's never the case, that there's some type of imperfection usually with the manufacturing and or the installation of these structures. And when we refer to the various codes, there are ways to consider these imperfections. And one of them is to outright directly model the imperfection in our FEA model. So I would like to show you now how we can directly model these imperfections and integrating it with the structure stability in that first buckling mode shape. When we go back to the navigator here within RFEM, you'll see a option within the folder called imperfections. And it should be known that imperfections is one of the available options in the base program. You don't need any additional add-on for this. But what we can do here is to create a new imperfection case. And under the imperfection type, we can choose buckling mode. What we can do is to either select a load case or a load combination. And if you remember, we carried out the stability analysis for load case number 2, that fluid load. And we can choose the relevant mode number 1. We can deform the mesh by scaling that mode shape. And so we see here the imperfection magnitude options down at the bottom where I can import in that buckling mode and scale it based on the X, Y, or Z directions. Now for our case, we have a round structure that's not necessarily in these global X, Y, and Z directions. So for this, we also have the spatial option where I can tell the program to scale that buckling mode shape a specific value that I input in here. So we put in something quite small like 0.03 feet. So again, what I'm trying to replicate here is, let's say, a manufacturing defect where we know that this tank wall isn't going to be perfect. So I'm going to deform the FE mesh before I apply any additional loads to carry out the static analysis. So now that we have created this imperfection case here, we're going to go back to our load cases and combinations dialog box. And under the design situations, we should be familiar with design situations. We go back in here to edit the definition type. Remember, we're carrying out according to a second order analysis. We previously activated the stability analysis, but here you'll see an additional checkbox option to consider the imperfection cases. And this is typically by default always checked on. So now when we go to our load combinations individually listed out, we see this imperfection automatically considered. So again, when we take a look at load combination number 2 here, we are going to first deform the mesh based on that buckling mode and the scaled magnitude that I had put in. Then we're going to apply the static loads, dead load, and that fluid load to give us a full static analysis result. So we can go to calculate all just to see what our results look like with this imperfection now considered. Again, the program is going to go ahead and carry out all of these load combinations here with that imperfection considered according to a second order analysis. So currently I am looking here at load combination number 2. So this is the dead load plus the fluid load. And sure enough, when I look at my deflected shape for the static analysis, I'm not looking at the stability analysis, but the actual static analysis, we see the deflected shape replicate here those imperfections where we have directly modified that FE mesh. In addition, we're probably also interested in the surface stresses. So we can activate here under our surfaces option, such as the von Mises stresses. And because of that deformed mesh as well, we're going to see slightly higher stresses at these particular locations where that deformed mesh is also applied. So these imperfections, again, can be really powerful in the sense of integrating with the structure stability add-on to outright model the imperfections, not only for surfaces, but we can also do so for members. Okay, so jumping to our second to last example here, I am going to focus in on a much smaller scale for the structure stability. So now I would like to turn to talk about steel connection design according to the AISC. You'll see here that I have a very simple model, and this is all carried out with one-dimensional members. If we turn this into wireframe view, and then we go back to the rendered view, what we have here is a simple W cross section for our beam at the bottom. And then we have a vertical pipe member shown here framing into this beam with a point load of 125 kips. Well, I have activated our steel joints add-on. So this allows us to carry out the connection design according to the AISC. Now, I've already input in all of this information directly for this particular node where these members are intersecting, and we can graphically see some of those components here. Just to mention, I previously did another webinar devoted entirely to steel joint design, so I'd certainly refer you to that on our website and YouTube channel because we won't be able to cover everything in just a few minutes here. But the powerful thing about our steel joints add-on is that it creates an FEA model underneath the hood, meaning that any connection is possible. We are not just limited to standard connections carried out with analytical equations, but rather, this is a pretty non-conventional connection here, and that FEA model is created underneath the hood to carry out the AISC design. What else this allows us to do, which you'll see here under types for steel joints, is that I actually have 3 different scenarios that I have for this connection design. And what I mean by this, if we go into the steel joint directly, is that my first scenario here is considering the connection with no stiffener plates. Rather, we just have an end plate here that is connected by bolts to the top of the beam flange. We have our pipe member, which is welded directly to that end plate, but again, no stiffener plates. Then I created a second scenario to compare where we have applied 2 stiffener plates. So you can see that additional component added here with the stiffener plates applied at the left and right of that end plate. And then I created a third scenario where we have that third stiffener plate that is going to be applied right at the center where that pipe is framing into the W section. So when we carry out the design here, we will go ahead and just open up the saved results. And of course, we're going to give you full design of the bolts, the welds, and the plates according to AISC. But we also have the ability to integrate with the structure stability add-on to carry out the buckling analysis of this connection. And for these 3 different scenarios, I see my buckling analysis results, and you'll notice that the critical load factor for the first scenario, no stiffener plates, is given as 8.18. And if we're further interested in seeing the buckling shape without any stiffener plates of this connection, we can go ahead and activate this option here in our toolbar to view the results in the steel joint. So I can scale this mode shape slightly where we can see this FEA model that was generated underneath the hood, and the actual structure stability analysis was also carried out so that we see that really buckling of the web is a concern for this particular connection. Now moving on to the second scenario where we have 2 stiffener plates, we'll notice here that the critical load factor is slightly higher at 9.83. And we'll go ahead and take a look at the mode shape here, considering 2 stiffener plates. And when we take a look at this deflected shape here, again, still a concern of the web buckling in between these 2 stiffener plates at the left and the right. And finally, we have our third scenario where we've added in this third stiffener plate, also shown here graphically. And you'll notice that the critical load factor jumps immensely to 31.79. So again, we can multiply our loads by 31.79 before we need to be concerned with any type of buckling with this connection design. And what you'll notice with the deflected shape here is that the stiffener plate itself is actually going to buckle before the web element does. So again, just these three different scenarios that allow us to see the buckling behavior kind of integrated with that structure stability add-on. So when you own both the steel joints add-on and the structure stability add-on, you by default have all of these results available to you. You have also the option in the lower left-hand corner to save the steel joint model. And what this means is that, again, the program's creating this 3D FEA model underneath the hood. So I went ahead and saved that just to show you what's kind of going on in the background. The bolts, the welds, all of the plate elements are created automatically by the program with this FEA model that you see here. In order to carry out the connection design. And in addition to AISC design, again, we're carrying out the stability analysis. So every example that we've seen up until now is the same workflow that's going on underneath the hood, where we can view here under the stability analysis results are 4 different eigenmodes, the critical load factor of 31.729 before we see kind of the buckling of that stiffener plate, and then also the relevant mode shapes here with slightly higher critical load factors. So again, we start to see concern for the buckling of these web elements. So pretty unique and powerful, again, about what's going on underneath the hood for, again, any connection type because of the ability to generate this FEA. All right, so the final thing that we want to go over here is instabilities. So we'll jump to our last example. And no longer are we going to focus in on the structure stability or the mode shapes of our structure, but let us kind of turn to the topic of instabilities. And instabilities are not unique to RFEM. They happen in any FEA program. The question is, do you have the necessary tools to kind of help you investigate where these instabilities are coming from? And the structure stability add-on can be incredibly helpful with this topic. So we have here just a general steel structure, again, modeled with all beam elements, and these come directly from the CSA standard this time with W250 by 80 steel shapes here, some HSS members, and so on. I also have some various applied loads. So we'll see the dead load applied here is an area load. We have snow load, and then we also have actually a couple wind loads in the global X direction and the global Y direction. And all of these are combined into load combinations here according to the NBC standard. So again, not really focusing on the stability design. I just want to carry out the design or the static analysis rather of the single dead load case. And by default, load cases are run according to a first order analysis. So I go ahead and run this calculation. And what we find with this first order analysis is our first instability. So we get a warning message in the program. And when we take a look at the table results down here, it tells us the stiffness matrix is singular. The structure is unstable in the direction of the global y-axis. Now, this red arrow here can certainly be helpful in a lot of cases where we maybe have a modeling error. If it's something a little bit more of a global instability, this red arrow is really just pointing to a single FE mesh point anywhere on the structure, so may not be as helpful in those cases. If we have ruled out any modeling errors and we're really unsure why we're getting this instability, what we want to do here is to go back to our load cases and combinations dialog box, just like what we've previously done to activate the structure stability add-on. But this time I'm going to go into the default settings here to modify this to calculate this eigenvalue analysis without loading for an instability check by mode shape. So load independent eigenvalue analysis. When I click calculate here for load case number 1, for the static analysis, we're sure enough still going to see that instability. But what we will also see now is the load independent eigenvalue analysis run. And we will begin to see what the problem is here with our structure. So if I increase this mode shape deflection, we see that the structure is just kind of free to hinge about its own axes in the global Y in the global y-axis. And that's just simply because we have pin supports everywhere. These member ends are connected with pin moment ends. So therefore, we just have no lateral bracing for this steel structure. In order to resolve that, let us create a few members here. So I'm going to draw a new single member. The member type will be tension only for this lateral bracing, and the cross section will just be a single angle that I've already defined here in the model. And I'm going to turn this into wireframe view where I can snap to this particular node. And the program asked me to clear my results, no problem. So what you'll see here is that the program automatically detects these snap points to allow us to create this cross bracing for this last bay shown on the right. Now, once we have modeled in this lateral bracing on the right-hand side of the structure, I can hold down my control key to select all of the elements. I can mirror this to create a copy about the YZ plane, and I can select my mirroring point at the top of the structure. And now we should see this lateral bracing applied at the left side of the structure in that last bay. So what we would hope then is that we can go into our load case 1 to rerun this calculation. So we'll cycle through the static analysis, and unfortunately, what we'll find again is another instability. So when we take a look at this new instability error, it tells us that the instability occurs here, where this red arrow is, around the global axis X. So again, we've kind of ruled out any modeling issues. We're really not sure what's going on, but I have left that structure stability add-on active for load case number 1. So I can simply turn on my results here, and sure enough, I see what the issue is. It appears that this column is not connected to the rest of the structure. So in this scenario, this red arrow is certainly helpful for identifying where that modeling error occurs. When I turn off the results here and I zoom in wireframe view, very, very closely, sure enough, I see that these two nodes are not connected. So I can simply take this node and I can go ahead and drag and drop it here to this other node connected to the frame. So what we should see now is hopefully the dead load will solve and we have no more instabilities for this load case. So assuming now that everything is solving for first order analysis for these first few load cases, we want to drop down to a load combination. And I'll start off with this load combination here, dead load plus snow load. And keep in mind, this is always run by default according to a second order analysis. So again, my load cases solve fine. We're moving on to load combinations. So I'm going to carry out this calculation, and the program will attempt to run this. And what we should find here is our third instability. So this time we can see here the structure is unstable around the global x-axis. Now, when I turn off the display of the loads here, we've really ruled out any modeling issues because those load cases under first order analysis solve perfectly fine. So we know that, nodes are connected, everything is fine there. What I would suggest doing for instabilities under load combinations, these are by default solved according to a second order analysis. So I would suggest, if you're getting an instability, is to change this to a first order analysis. In addition, we can activate this structure stability add-on, but I'm going to go in here into my definition type, and I'm going to carry out the standard eigenvalue analysis with 4 eigenvalues to solve for. So we would hope then that we'll go ahead and solve load combination number 2 here, that the first order analysis will solve okay. And actually what we see here immediately is that no errors are shown. The structure solves just fine under first order analysis. So what could possibly be the problem then with second order analysis? Well, I toggle down to my stability analysis results, and we immediately see what the issue is. The 4 eigenvalues that we solve for have a critical load factor of 0.67 with the relevant buckling mode shape for these very slender columns shown here. Anything under a value of 1.0 is always a problem. This means that the structure cannot take on 100% of the applied loads and load combination number 2 before it's going to fail, as we see here. If we take a look at the other relevant mode shapes, it really has to do with these slender columns. So clearly we need to make a change to our model because it cannot take on the applied loads. So we're going to select here all of our vertical columns that are very, very slender. We'll go ahead and double click them, and under the section, we're going to modify this. Instead of a HSS 51 by 51, we'll change this to an HSS 127 by 127. So when we click OK, let us take a look at here, the model. And even in the rendered view, I think we can all agree that this looks like a much more applicable section than that very slender HSS. So I'm going to go back to the load combination 2, and I'm going to change this to a second order analysis, which again is what we would hope to carry out considering P delta effects. We can leave the structure stability add-on active here. And now, hopefully, with these more robust sections, we should see the full static analysis solve here for second order. And sure enough, we see the calculation carry out just fine. We can turn this into wireframe view. So we see all of our static analysis results. And we also toggle down to the stability analysis. Now looking at the first 4 mode shapes, we still have buckling here of these columns, but the critical load factor is now 17.48. So we could probably say that this failure of these columns is not a concern because the structure can take on 17 times the applied loads from load combination number 2 before we would see it fail, as we show here within this first mode shape. So again, the structure stability add-on not only can carry out the buckling analysis of our structure, but also we can utilize it to help us with those modeling errors and instabilities. All right, so we will go back to the PowerPoint here to conclude our webinar. This presentation was recorded and will be available on our website on the same page that you registered for the webinar. I have already uploaded all of the models that you saw in the example today, so I'd encourage you to request a free download for a 90-day trial version of RFEM 6. So this is full capability for 90 days. It includes all add-ons like structure stability, 7 degrees of freedom, steel joints, and you can open up the models that I use in that presentation directly within the trial version. If you have any questions about today's presentation or anything else, feel free to contact us in our Philadelphia office. Our phone number is 267-702-2815, and our email shown here at the bottom is info-us@duluwal.com. We will have many more upcoming webinars. We hold these approximately once a month. You can register at duluwal.com under support and learning webinars. As most of you know, I tend to send out a reminder email about a week before these take place, so just keep an eye out for those for the next webinar invite. PDH certificates will automatically be emailed to all participants who are here for the full presentation. So that is a requirement of the states that we are pre-approved providers, that you are here for the full 60-minute duration in order to receive that PDH. If you watched with a colleague or in a conference type setting and you yourself did not register for this webinar and you would like PDH and we're also here for the full presentation, feel free to request that by sending us an email at info-us@duluwal.com. Again, if you yourself did not register and you are here for the full presentation and you want that PDH, please send us an email here. The PDH is not automatic after this webinar ends. It usually takes about a day before those will be emailed to you. So again, keep an eye out in your email within the next day to receive that PDH. As always, I want to thank everyone for attending, and we hope to see you at our next presentation. Thank you.